This is my old 3D printer. I got it about 4 years ago, and I've gotten a ton of use out of it. But lately, it's just been collecting dust. Ever since I upgraded, it's been sitting in a dark closet, out of sight and out of mind. I think it's time to turn it into something useful. Here's the plan. I want to turn this into a robotic camera rig. One that can glide through pre-programmed motion paths for cinematic, repeatable shots. Kind of like a turntable and a camera slider combined. And here's the bonus. With an automated remote shutter, I can also use this to scan real-world objects and create detailed 3D models using a technique called photogrammetry. But why use an old 3D printer to build this? Well, think about it. It's got precision stepper motors that should be powerful enough to move a camera easily. It already moves around in 3 axes, 4 if you count the extruder. It's programmable using G-code, and all the hardware is just sitting here waiting to be repurposed. In other words, it's practically begging to be transformed into a robotic camera rig. So a while back, I picked up this big circular bearing. My thought was that something like this would allow the camera to rotate a full 360 degrees around an object, making it possible to scan larger, heavier items, or even shoot around something that can't be moved at all. The plan was to mount that bearing ring to a large base with a hole in the center so that the whole rig could be wrapped around whatever I was scanning. From there, I'd attach a long metal arm that would extend out and hold a small motorized cart. That cart would slide forward and backward to control the camera's distance. Mounted vertically to that would be another piece of extrusion to raise and lower the camera. And finally, there would be a motor to tilt the camera up and down. It sounded great on paper, as many things often do, but let's just say I ran into some issues, which I'll get into later. But for starters, I decided to break this project down into steps because it was obviously going to be fairly complex. But you know what doesn't have to be complex? Protecting yourself online. When you use the sponsor of this video, NordVPN. I grew up during the golden age of the internet. You know, back when we still thought that cats eating cheeseburgers was peak comedy. What can I say? It was a simpler time. But the nice thing about it was that it felt really private and anonymous. But now, we've got governments trying to censor social media. We've got corporations region locking their content for no apparent reason. We've got scammers empowered by AI. Point is, things are a little bit crazy out there on the good old World Wide Web these days. Luckily, NordVPN is here to help. NordVPN lets you set your country and city to get around region-specific restrictions, so you can access your favorite content wherever you go. Pretty handy. Nord keeps you safe by hiding your IP from the sites that you visit. There's even an optional feature called Kill Switch that automatically disables your internet connection in the event that you get disconnected from the VPN, so that your data is never exposed by accident. NordVPN's Threat Protection Pro scans your system for any malware you may have picked up, and it stops malicious files from getting downloaded in the first place. Plus, it blocks trackers and alerts you if any of the sites you visit are known for scams. One feature that I personally love is MeshNet. It allows you to easily and securely transfer files from one computer or mobile device to another. Which is great for me because I keep building more and more computers. Seriously, I have a problem. But with NordVPN's MeshNet, at least transferring files between them is a breeze, and you can have up to 10 devices active on one account. Start protecting yourself online today with NordVPN. Use the link nordvpn.com/benmakes or just click the link in the video description. There's a 30-day money-back guarantee, so why not give it a shot? Again, the link is nordvpn.com/benmakes. And thanks again to NordVPN for sponsoring today's video. First, I would tackle the tilt and elevation axes, because the solution to those seemed the simplest. These two are kind of a package deal, since the part that holds the camera itself directly connects to the vertical motion system. So I designed these together at the same time. On the 3D printer, there's a stepper motor with a pulley that's used to move the X-axis left and right. I figured, why not reuse that to tilt the camera up and down? So I designed a U-shaped bracket for the camera to sit in, and bolted a 60-tooth pulley to the side. That'll connect to the motor via a smaller pulley, giving me a bit of gear reduction for smoother movement and a little more torque. The existing Z-axis, which moves the print head up and down, has two 2040 aluminum extrusions that serve as tracks for 3 little V-shaped wheels on either side. On the left, this linear rod, which is connected to another stepper motor at the base here, is what actually moves it up and down. So I decided to basically take these two, rotate them both 90 degrees so that they run side by side, and have the screw be in the middle. The camera mount will be held between 2 side plates mounted to these existing printer parts. I could have gotten rid of these entirely and incorporated the wheels into my new side plates. That would have probably been the more professional way to do it, but I wanted to reuse as many things as possible and keep the manufacturing simpler and cheaper. As a result though, the existing motor shaft didn't stick out quite far enough. Luckily, I was able to take the unused extruder motor, which is a little bit longer, and fit a new 20-tooth pulley to that. In order to space these parts equidistantly and provide more rigidity, I purchased and cut down some 2040 extrusion for this end and some 2020 extrusion to go here. To keep everything accurate and avoid slamming an expensive camera into the rig, I needed limit switches. Just like on a 3D printer, this setup needs to home itself every time it powers on, setting the 0 point on each axis. The Z-axis doesn't need any changes. It's already got a working limit switch from the original printer. But for the tilt axis, which used to be the X-axis, I added a small micro switch that triggers when the camera tilts all the way down. I went through a ton of iterations to get this whole assembly right. The 3D printer was definitely going burr. And I even jumped the gun a little bit by ordering some aluminum plates before I realized I had overlooked a pretty obvious issue. This tilt mechanism only let the camera point downward about 45 degrees. That's fine for a lot of shots, but not if you want to look straight down on an object, which would be useful for photogrammetry at least. Pretty stupid, but what can I say? I got excited. The final version looks like this. It allows the camera to tilt a full 180 degrees. 90 up, 90 down. It's super rigid, and yeah, a bit heavy, especially with the camera attached. But like with the CNC machine, rigidity is key if you want smooth, wobble-free motion. Next up was the Y-axis, the part that moves the camera forward and backward. I was a little bit worried that the tilt assembly that I had just built might be too heavy for the original motion system since it's belt driven. I seriously considered swapping it out for something more rigid like a linear rail setup, but after drilling a few new holes and bolting everything to the small cart that used to hold the heated bed, it was performing well in testing. The original 4040 extrusion only gave me about 220 millimeters of travel, which is way too short to be useful. So I bought a longer piece and cut it down to 750 millimeters. That number was kind of arbitrary, but it felt like a good compromise between reach and stability. While I was at it, I cut some longer Z-axis rails and picked up a longer lead screw. Of course, with a longer Y-axis, I also needed a longer belt. Thankfully, GT2 belts are a standard off-the-shelf product, so I just cut it down with some scissors and crimped on these brass bands. I was also able to reuse the original tensioning system, which worked perfectly. Okay, that was fairly easy. Now for the hard part. Now, as I mentioned earlier, I really wanted to use this big ring for the rotational axis, but the more I thought about it, the more I realized that it was going to be kind of difficult to actually drive the thing. I had two major options, and neither one of them were particularly great. 1. Use a tightly fitted rubber friction wheel to spin it from the inside. But with all the added weight, that setup seemed very unreliable. It seemed like it would be easy for the rotating components to slip and lose position. 2. Machine a huge internal gear to mesh with the smaller drive gear. That would have been more precise and reliable, but I don't really have the tools to make something that large and accurate, and getting it custom made would be pretty expensive. Also, it's surprisingly hard to get super accurate measurements of a ring roughly 18 inches in diameter. I mean, look at these calibers I have to work with. Oh yeah, and then there's the fact that either one of these setups would be extremely prone to getting its wires tangled. So for these reasons, I decided to pivot. Yeah, you see what I did there? Pivot, because it's a turntable, and so how about this? Instead of moving the camera around the object, I just rotate the object. As far as the camera is concerned, it's almost the same, but there is one key difference: the background. With a moving camera, the background shifts with each angle. With a rotating object and stationary camera, the background stays the same. That said, this setup simplifies a lot of things, especially when it comes to wiring. No rotating camera, no tangled wires. The most straightforward plan would just be to stick a large round plate on top of a stepper motor and call it a day. And I guess you could do that, but I don't think it would work very well. These little NEMA 17 motors really don't have that much torque. You can stop them with your hand. But I did want to stick with NEMA 17 because that's what the control board is set up to drive. If I tried to bump it up to something like this NEMA 23, yes, I'd get way more torque, but I'd also have to add more driver components and the whole thing might get messy and overcomplicated. Initially, I opted to just use one of the same 3-to-1 gear reduction pulley systems that I used for the tilt axis, since it seemed to work pretty well there. That pulley would mount to the bottom of a plate that would sit on a smaller bearing ring. The bearing would then be mounted to some standoffs, connected to a bracket that would be bolted to the bottom of the Y-axis extrusion. This system worked, but it was pretty weak. Even with a 3-to-1 gear reduction ratio, the turntable couldn't handle heavy objects or any real rotational resistance. After doing some research, I found that you can buy NEMA 17 motors with built-in gearboxes. Most of these had super high ratios, like 27:1, which would be pretty slow, but I did find this one that's only 5.18:1.
Oh yeah, that thing is nice and beefy.
This dramatically improved the power, and it was still plenty fast. Now a word on the turntable plate itself. This is about 9 inches in diameter, so big enough to actually serve as a decent platform in and of itself, but I also added these 4 holes. These can be used to add a larger platform, like a big circular piece of wood, for example. Up to this point, all of the custom parts I used were 3D printed, mainly because I was still constantly revising things. Now, as usual with this type of project, it took me a ton of attempts to get everything fitting together just right. But I wanted to take things to the next level. Not just for the extra rigidity, but also to give everything a polished, professional look. These parts were provided to me by JLC CNC. I simply uploaded my files to JLC CNC's website, and they machined, bead blasted, and anodized each component. If you need high quality custom parts that are not only super accurate but also look great, check out JLC CNC. So that just about covers the main design of this device, minus a few add-ons. Let's get it put together and see how it works. First up, assembling the tilt and elevation module. The machined metal side plates bolt on easily, just like before, and the U-shaped camera bracket drops into place between them. To support the rotation, I used these bearings. The idea was that I could tighten down a nut on the end and still get smooth motion. But as you can see, there's still a bit of binding between these two bits. It's a pretty minor issue and everything still functions fine, but it's worth mentioning. I hadn't noticed this in the 3D printed version because the plastic was flexible enough to hide the misalignment. I also had a new Y-axis plate machined. The original one didn't center the camera properly, and that matters because both of my camera's mounting points aren't centered on the body, they're right underneath the lens. So I offset the carrier plate and the turntable mount to keep the camera pointed straight down the center. The whole tilt, elevation, and distance module just slides right onto the 4040 extrusion. As I mentioned earlier, I did extend the Z height by cutting some longer 2040 rails, and I also bought a longer lead screw, but unfortunately this didn't fit on the existing brass nut since it had a different thread pitch. So I had to drill some holes and mount the correct one to the metal bracket that moves the whole thing up and down. That did unfortunately mean that I had to take the whole thing apart and reassemble it. These kind of projects can really be an exercise in patience, I'll tell you that much. The turntable gets assembled separately. The motor bolts to this plate, which is held by 4 standoffs. I designed this to have some adjustability for length by using slots instead of holes. 4 larger standoffs screw into the main ring and secure it to the base. Meanwhile, this 60-tooth pulley gets bolted to the bottom of the turntable platform using 3 small screws, same setup as the tilt axis. It's a little tricky. You have to loop the belt over the motor's 20-tooth gear and the large pulley before you bolt it onto the ring from the top. Finally, the entire assembly attaches to the main frame using 6 M4 T-slot nuts from underneath. Now let's talk a little bit about the electronics. The whole thing is controlled by a stock Ender 3 mainboard. This is still mounted underneath the original printer frame. Luckily, this board supports 4 motor drivers, including the one that was originally used for the extruder. Here's how I repurposed them. The X-axis now controls the camera tilt. The Y-axis moves the camera in and out. The Z-axis handles vertical height, which is basically unchanged, and the extruder driver now controls the turntable. The limit switches are simple, just plug them into their usual ports. I did have to splice in some longer wires to reach everything, but that's about it. Now technically, this setup will work right out of the box. Sort of. You can jog each axis manually, and the camera will move more or less as you would expect. But if you try to run a program, things are going to fall apart quickly, maybe literally. This is where Marlin comes in. It's an open source firmware that powers many 3D printers, and it can be customized pretty easily. First up, we need to update the firmware settings to match the new physical layout. Since I extended both the Y and Z axes, I had to increase their soft limits in Marlin. And for the X axis, which now controls the camera tilt, I actually needed to reduce the travel limit to stop it from flipping over and wrecking the camera. Next, steps per millimeter. This setting tells Marlin how many motor steps it takes to move each axis 1 millimeter. But for the X-axis, now a rotational axis, it's really moving in degrees, not millimeters. But for simplicity's sake, I'll just pretend that 1 millimeter equals 1 degree and factor that in when programming movements. Still, it needs to accommodate the new 3:1 reduction ratio. We also need to fix the extruder settings, aka the turntable. Once all of the settings were updated, I built the firmware using VS Code, saved the .bin file to a micro SD card, and inserted it into the printer while it was turned off. After powering it back on, it flashed the firmware and everything seemed like it was working. Soft limits updated, motors moved, but the turntable was not really moving as expected. No matter what I tried, it only rotated about 2/3 of the expected distance. I redid the math over and over, in my head, on paper, on a calculator. Nothing made sense. But then I noticed something. Marlin's default steps per unit for the extruder was 93. I had calculated that I needed about 138.13. If you divide that by 93, you get 1.48. So basically, it thought it was going 50% further than it was. To make a long story short, apparently you have to send a special G-code command to clear the printer's EEPROM, which I totally knew. I mean, who doesn't know that? It's obvious, right? Anyway, I think it's finally time to feed it some programs. This thing still thinks that it's a 3D printer, and that means it operates off G-code, machine instructions to move to specific coordinates sequentially. I downloaded a program called Pronterface onto my CyberDeck, which I'm using to control this machine. This can not only allow you to jog it manually, but also load G-code files and send them over USB. Of course, the SD card slot still works for that too. To generate the code, I wrote a couple of Python scripts. This one is for photogrammetry. Photogrammetry is a method of 3D scanning that works by stitching together a bunch of still images taken from different angles. Now, for video, I can just hit record and run the program. Easy. But for photogrammetry, I wanted the system to automatically trigger the camera to take still images at each position. Now, here's the cool part. You can actually do that with G-code, but you will need an output pin to trigger the camera. So I flipped the whole machine over again and took another look at the control board. My first thought was to repurpose one of the PWM-capable fan outputs. Since I'm not using a hot end or extruder anymore, that fan output was just sitting there. But there was a catch. It puts out 24 volts. Not ideal. Also, I may or may not have slightly fried the MOSFET while experimenting. Luckily, I found a better solution anyway. There's a 5-pin connector on the board meant for a BL Touch, which is an auto bed leveling sensor. It includes a 5-volt power line and a signal pin. With a small tweak to the Marlin firmware, I was able to repurpose that pin to be a custom output. Many cameras, including mine, have a remote shutter port, but I didn't want to just wire the camera directly to the printer. And also, this camera needs to focus first, then trigger the shutter, which makes things a little bit trickier. So here's what I came up with. And yes, those are huge overkill mechanical relays capable of switching mains voltage, and I'm using them with 3.3 volts. When the printer sends the signal, the Arduino immediately activates the first relay to trigger the focus. And then it waits about half a second, then fires the second relay to take the photo, then resets both. This way, everything is electrically isolated, because I really can't afford buying another new camera. I got these rubber feet attached to M5 bolts. They provide support for the heavy turntable, which otherwise has an unfortunate tendency to do this. I also picked up this cable chain to keep things tidy, and printed a mounting bracket for it. Along with that, I printed a box for the relay trigger system, and mounted it to the frame, and also printed another custom bracket for the screen so that I could relocate it to the side of the machine where it would be easier to use. Here's what the completed machine looks like. It ended up being a little bit larger than I thought, but I wanted to be able to photograph and scan larger objects, so I designed it to accommodate turntable sizes up to 18 inches. That meant that the Z height also needed to be pretty tall in order to maintain the ability to look down on things with the camera. The maximum forward travel is about 600 millimeters, with the smaller turntable size, that is. And for the Z axis, it's about 500 millimeters of travel. The camera can also tilt up to 180 degrees. You do have to be a bit careful with this, and make sure that the Z axis limit switch is high enough that longer lenses won't hit the bottom during homing operations. It can actually move quite quickly, but it's better to keep things slow and steady for the sake of eliminating camera vibration. If you want the video to be faster, you can just speed it up in the editing software. Most of this is pretty rigid, although I will admit that I don't like how the Z-axis has some horizontal play. This is mostly due to the use of these rubber wheels in the base. There's no reason any force would be applied in that direction during normal operation though. Still, I think it's an area that could be improved. Now, let's see it in action. Alright, I'd say that's working pretty well. Now let's take a look at some of the 3D models that I was able to generate using photogrammetry. I got some pretty good results here. The two programs I tried were Meshroom and 3ds Zephyr. Both managed to generate decent models and textures. I'd give a slight edge to Zephyr, mainly because of the textures and the mesh seems a bit less bumpy, although it might be less detailed as well. Different parts of the model came out better using one versus the other. The models look really good at a glance. If you zoom in, you'll start to see a few issues, mostly with where the objects touch each other. The main issue, though, is that reflective objects cause issues, but these things can be improved with a little bit of cleanup work in Blender or any other 3D program. The main limitation of this setup is the constraint on size and weight, but with the 18-inch wood table, I feel like this covers most household objects that you would want to scan. While it's far from perfect, I'm pretty happy with this build, and I plan on using this to showcase things that I create on this channel in future videos. Let me know in the comments if you have any suggestions for improvements. Thanks for watching!